So I want to start with a really, really big question, which is the question of how people learn. One of the sort of things that distinguishes sort of human cognition from all of the other learning systems and thinking systems that nature has ever built is the number of ways, the sort of flexibility of our ability to learn from data, right? So when we're little kids, when we're lying in the crib, we're learning just from sort of observing the world, and over time we're learning by interacting with our environment, by observing other agents interacting with the environment and trying to figure out what it was that they were doing. And once we sort of understand our physical world and understand our social role within it, we start to learn language. And once we've learned language, right, it's language that really allows us to do most of the other things that, the sort of complex skills that we acquire in adulthood, right? We learn facts about the world, we learn procedures, we learn things that even extend our knowledge of language itself. I would guess that most of us who are in this room today, right, got here by doing things like reading books and talking to colleagues and things like that. It's really just in the last couple of years that we've been able to do this kind of learning in the machine learning world as well. And so what I'm going to do today is give you just like a very, very high-level overview of what some of that work looks like. And I'm going to start actually with the problem of writing code itself, right? So obviously there's been a huge amount of interest just in the last year or two in using language models as tools for program synthesis, starting with natural language descriptions of programs and mapping to sort of working code for these programs themselves. It turns out that in addition to sort of using language to specify what program you want to write, we can also build systems that learn how to program from text, right? That learn from instructions about sort of what kinds of reusable high-level functions and primitives and refactoring operations are likely to be useful in order to build systems that can write their own code. And so in conjunction with a bunch of other folks at MIT, we've been doing this and using systems, right, that not only sort of follow natural language instructions, but learn from language what the right abstractions are. We can do well on a bunch of cool program synthesis benchmarks and actually turn this back into sort of question answering systems themselves and build systems that are better at answering natural language questions using these coding abstractions that they've written. Another domain where this kind of learning turns out to be really important is sort of sequential decision-making, things like robotics. So we now have models that we can teach to build high-level plans, right? Translate from goals like put the knife into the drawer into a sequence of steps that you would need to follow in some sort of household environment in order to accomplish that plan by just translating these goals into plans expressed in natural language and then using models that sort of execute each of these natural language skills to take some actions in a low-level world. So here's an example of a system like this, sort of in action and simulation. We start with a goal, we generate a natural language plan, and then we can sort of move through the environment to execute this plan. And maybe what's most exciting about these kinds of approaches is that they allow us not just to do well at these planning tasks, but to generalize from very, very small amounts of sort of robotic demonstrations in ways that we really couldn't hope to before, right? So we can take this model and we can give it objects that it's never seen before, we can give it goals that it's never seen before, plans that require sequences of actions that it was never trained on. And because we know how to reason about those goals in natural language, we can then reason about those goals actually down at the level of low-level action as well. Finally, one sort of new direction that I'm excited, or not finally, but one other new direction that I'm excited about here, thinking back to the sort of dictionary example that we were looking at before, is using language to actually change the way we train models of language themselves. And so we've been developing techniques that allow you to do things like control model generation, using natural language descriptions of things that are true in the world. You can do some sort of fun things with this where, for example, you update models' knowledge about the world globally. You can get them to think that the CEO of Google actually works at Apple and various things like this, just by specifying the kinds of updates that you want to make to these language generation models themselves in the form of natural language. One other thing, and maybe the last sort of application of these kinds of techniques that I want to talk about here, is language not as a tool for sort of training models, either in language domains or in other domains, but actually as tools for understanding the computation that's going inside these models. And so we've also been developing techniques that allow you to, for example, pick up an image classifier, label the individual features that are being used by that individual, or by that image classifier, the neurons in a big neural net, with natural language descriptions of the computations that they perform and of the sort of role that they occupy in the larger computation that's being performed by this model. And so we can generate these nice descriptions that sort of give us a high-level picture of the sorts of features that are important for specific decision-making tasks. But maybe more importantly, we can actually use this understanding to make models themselves better. right? So one thing that's observed in a lot of image classifiers, images on the internet have both sort of visual content and also text, and sometimes the models pay more attention to the text in the images, such that if I take an image of a ship and I put the word car in the corner, it actually gets classified by a model as a car rather than ship, or this frog getting classified as a chihuahua. Using the techniques that I was showing you before, we can actually reach inside these models and figure out which pieces of them are responsible for looking at the text rather than looking at the contents of the image, and just cut these pieces out. And when we do this, we can actually significantly reduce model sensitivity to these kinds of spurious feature correlations, sometimes getting all the way, or about half the way back up to the top level performance of these models. And so language is a tool not just for sort of training models, but actually interpreting them and sometimes improving them directly, again, in domains not just involving languages inputs, but also these kinds of visual domains as well. Finally, another sort of high-level area of research going on in our group right now is just understanding how these language models that have driven a bunch of the applications that I showed you before actually work under the hood. And so my student Ekin, in collaboration with some folks at Google, has been doing a bunch of sort of foundational work here on understanding just how in-context learning, few-shot learning, various other impressive capabilities of big transformer language models actually work under the hood. And I will wrap up there. As always, all the sort of credit here to the students who actually did the work, and thank you all for your time.